Okay, hello, welcome to my channel. Now in this video, we want to find the product of a, b, and c, given that the antiderivative of this function is just this part, that is the arbitrary constant plus this functions of x, right? Okay, so this question is from the JEE Main indefinite integral math question, right? And to find what the product of these three constants will be, take note a, b, and c are constants here, all right? We usually start by taking the antiderivative of this function, and then we compare the antiderivatives, right? Thereby getting the constant a, b, and c. Good. That is the, in fact, normal way to approach this question. But in some cases, that usually takes a lot of time, right? And you may need a little bit of a trick to get around this. And the little thing you can do, which is different from the usual way, is by taking note of the fact that the derivative of this antiderivative will give you back the integrand, that is the primitive function, the integrand here. So if you can differentiate this antiderivative, even in this general form, and then you try to get back to this original function, in the process you will figure out what your constants a, b, and c are, and from there you can find this product. Okay, so let's just see if that's really worth it, because that way may not really guarantee your result, or maybe a shorter time of finishing, because after differentiating it may not really look like, and it may demand a lot of steps before you can get back to this original expression, that is the integrand here. And some cases the integral is always easier to deal with, so you can just go ahead and try it straight. But let's just see how we can use the trick in this particular question. So as I said, we will start by differentiating the antiderivative given. All right, so let's put it here. Say by differentiating, okay, so let's say maybe let's differentiate the antiderivative. All right, so let's call the antiderivative just anti-d, where the d stands for derivative. All right, okay, great. So if you do that, you notice that the derivative of this arbitrary constant will just be 0 plus the derivative of this part. So it's going to be 1 over, right? So it's going to be 1 over 2 times the square root of a. Okay, we multiply it by the derivative of this part. So let me just do this. We notice this is inverse tangent function. When you differentiate inverse tangent of an angle, we will have something of this form. We will have maybe 1 over 1 squared plus the square of this inside, which is b squared, then the tangent squared of x, right, divided by the square of the square root of c, which is just in fact c. So we usually have 1 over 1 squared plus the inside here squared when we are differentiating inverse tangent function. But you notice that this inside here has another function of x, this tangent of x. So in fact, we will use the chain rule here by differentiating the outside function, which will give us this, and then we'll multiply by the derivative of the inside function. So let's see what the derivative of the inside function will be. Well, when we take the derivative of b over the square root of c times the tangent of x, taking note that b and the square root of c are constants, so we are just going to put it out front as a constant multiple, that is b over the square root of c. Then we multiply that by the derivative of tangent, which in fact is secant squared of that same angle. All right. Okay, and you notice this is just x. In fact, we can stop there, the chain rule there. Okay, so let's try to simplify this expression, and hopefully we can get something of that form. Okay, very nice. So let's start by saying let's multiply numerator and denominator by c, right? Because I want to clear this fraction at the bottom. So this will give us, well, let's just put this down, 1 over 2 times the square root of a. We multiply this with that. Notice this is c here. We have a square root of c under the b. That means we are going to have b times, inside this bracket, we're going to have b times the square root of c, right? Then we multiply that by secant squared of x. And we say that divided by, well, we multiply c by this denominator. C times 1 will just be c. Then plus c times this fraction will just give us b squared. Then the tangent squared of x. Okay, where this c and that c will cancel. Very nice. So you notice c times 1 over the square root of c will just give us the square root of c at the top, multiplied by b. Very nice. Okay, so let's see what we have. Well, From here we can rewrite, this is secant squared and this is tangent squared. You know, secant is the same thing as 1 over cosine, so secant squared will be 1 over cosine squared. Tangent squared will be sine squared over cosine squared. In fact, we're going to have 1 over 2 times the square root of a. Okay, so you notice again that this is square root of c divided by c. Okay, and that, anyway, let's just continue. So this is going to be, maybe let me put this b square root of c outside the bracket, right? Okay, so we're going to have secant squared is 1 over cosine squared, 1 over cosine squared of x. Then we said that divided by c plus b squared. Then the tangent squared is sine squared over cosine squared. Right, very nice. And now we can multiply top and bottom by cosine squared just to clear the fraction. So we're going to have b, then the square root of c, right? When you multiply this numerator by cosine squared, we'll just be left with 1 there. And then we multiply this denominator by cosine squared. In fact, we're going to have c times the cosine squared of x, right? We add it with b squared times sine squared of x, right? Okay, nice. So as you can see, we are getting the form that we need, which is this integrand, right? Where the numerator is just 1, and then the denominator is something really nice. This is 4 sine squared. We have b squared sine squared. So if b is 2, it will make sense, and if c is just 5, it will make sense. But then if that is the case, this right here has to be 1, all right? So this is where we try to make some observation. We see that 1 is there, which is just the 1 at the numerator, all right, coefficient of the dx. Then c cosine squared of x. C here can be called 5. Then b squared sine squared of x. B here can be called 2, so that when you square it, we just have 4. Which tells us that this right here should in fact be just 1. So if we say from the comparison, we say, okay, let's see, right, which is the coefficient of cosine squared, be 5. We let b, which is the coefficient of sine squared of x, or we let b, whose square is the coefficient of sine squared of x, to be 2, right? You know, that is what it would mean. If b squared is said to be 4, well, b can either be 2 or negative 2, because b is just an unknown. But let's just keep it at this and then see if this right here will just give us 1. Okay, great. So we notice that if we get c to be 5 and then b to be 2, then that means that this right here, which is b times the square root of c over 2 times the square root of a, you notice that for this to make sense, this has to be 1, right? Will be, well, b is 2 times the square root of 5 divided by 2 times the square root of a. So if we cancel this and that, that means that a has to be 5, in fact, for this to become 1. So that seems as if we have the constant we need, that we need a to be 5, we need b to be 2, and then we need c to be 5. And if we have that, in fact, this right here will be 1 over 2 times the square root of 5, then the inverse tangent of 2 tangent of x divided by the square root of 5. Well, you can find the antiderivative of this function to just compare to know if these constants are correct. But in fact, they are in their right positions. That is to say, a should be, this is c, right? If you solve that, this is exactly what you are going to get. But this right here is a little bit dangerous, because there is still a way we can multiply this denominator with this denominator, and things will be arranged without this place being 1, right? So I would like to get your opinion on what you think. If this method really worth it, or if we just have to go ahead and integrate this accordingly. But keeping in mind that taking the antiderivative may waste your time. But from here, you can easily find a product, which is what we are asked to find. You multiply the 3 of them together. In fact, this is just going to be 50, right, when we multiply. You notice 5 times 5, 25 times 2, just be 50, right, as the solution. But what really matters here is the method. But it makes sense, as it gives us the result a lot more faster than having to find the antiderivative of this function. But if you can have enough time, you can always compare your results, or maybe go ahead and do this straight as it is. Anyway, I'm not going to end the video here. Rather, I'm going to write another question that has this form. And the reason is, I want to show you that there are some times that this may not help. In that, after taking the antiderivative of this function, right, the result is always a lot more different from the integrand, and it requires a lot of steps for you to actually get back to the original integrand in order to get the constants. So in such cases, it is preferable that you just go ahead and integrate this immediately. Anyway, okay, the length of this video is already too much. In fact, the next video, okay, I'm going to give us another question so that we compare the two, and if you can also put in the comment section for us to know if this method actually works it. Anyway, alright, thanks for watching, and please subscribe to my channel.